So let's go to our second speaker of this afternoon. Great pleasure to introduce Kenneth McLaughlin from Tulane University. Okay, he's already thanking Carlos, but that's okay. We all thank Carlos all the time, right? Continuously. So, asymptotic analysis of multisoliton solutions, soliton gases. Ken, please.
Thanks, Andre. I should scroll to the end to start by thanking Carlos, but maybe first, it's a pleasure to be here, and thank you to the organizers for organizing this. Ricardo especially, thank you for all of your efforts. Thank you, Carlos, for many, many things. I thought I should start with one particular thing, which was in 2003, I visited PUC-Rio for a semester, and it was a wonderful experience. Carlos arranged for me to teach in Portuguese an introduction to probability theory class, which was a baptism in fire. He kind of expected that I had a non-existent Portuguese, and that maybe it would help me to teach this course. I learned, though, along that semester that I was picking up Carlos's manner of speech a little bit, and so I would speak to my parents-in-law, and they would say, "I haven't heard that phrase since 1962," and so I've lost that ability. But anyway, it was fantastic, Carlos, and thank you for many conversations along the way. And I'll start with just one photo. Carlos visited us in Tulane, and here is Carlos giving a lecture. You can see the total lattice kind of in the background there. And then there may be another picture at the end, okay? So I would like to tell you about integrable nonlinear partial differential equations. And these will be the three players in what I'm talking about. And I will talk about soliton solutions, okay? So the classical fundamental nonlinear modes that solve these partial differential equations. And but not just a single soliton solution, but something called multisoliton solutions. Okay, each of these equations, the nonlinear Schrodinger equation, the Korteweg Vries equation, and the modified Korteweg Vries equation, are examples that possess not just single soliton solutions, but multisoliton solutions. So we all probably know what a single soliton solution is. We saw them in Andre's talk. A simple kind of exponentially decaying mode which propagates without changing its shape down the spatial axis. Okay, but what I want to talk about is actually multisoliton solutions. So I should go to full screen, right? There we go. Okay, thanks, Carlos. Focus on the upper left-hand corner of the screen. What you're looking at is a solution, initial value, actually initial data for the modified KdV equation, and there are two peaks there. This is what we're going to watch evolve as a two-soliton solution, and so maybe we'll just watch it evolving once. So when these two peaks are far apart, they propagate just basically like traveling wave solutions, and then there's this interaction region, and after the interaction, they're again propagating essentially as they separate away. They become exactly two well-separated soliton solutions. Okay, so I want to watch it flow one more time. Focus on the upper left-hand corner, and I'm going to put the mouse at the peak of the smaller soliton, so you can watch what happens. This after the interaction, I'm not moving the mouse, but you see that peak has been shifted backwards to the left, right? That's a canonical feature of the interaction of solitons. They call it the interaction of solitons as though we're talking about particles. And that's an important thing to point out, is that there is a dual interpretation of this collection of solutions as particles and also solutions of the nonlinear partial differential equation, okay? What is the upper right-hand plot? That's the plot of the position of the tall peak as a function of time. Okay, so time is moving in the right, and the position is increasing. The vertical axis is the position of the tall peak. And then the lower left-hand slide is a plot of the velocity of that tall peak. And this is the acceleration, okay? So I'm showing you this so you think really right from the inception of sort of integrability, the discovery of solitons, there was an interpretation of them as particles. Okay? As long as they are far apart, that interpretation makes good sense. Okay? So here is a picture of what I just showed you, but from the point of view of maybe Zakharov or a physicist's point of view. You've got a space-time plot, time moving to the right, and the reddish curve, the thicker reddish curve, that is supposed to be the taller soliton, okay? And as long as it's far away from the blue curve, which is the shorter peak, then it's basically straight line motion because it propagates without changing position or changing shape, okay? Then there's this region where the two are interacting, you can't really identify the peaks. And after the interaction takes place, of course, they emerge, one propagating with the same velocity as it had before, and the other propagating with the same velocity that it had before, but there's been a shift in their position. So that's the picture I'm showing you there. So what you should think is, oh, that's like a collision operator being described, but coming from the analysis of a nonlinear partial differential equation. Okay, so that's the kind of story. All right? But I want to stress that it's an interpretation of a solution of the partial differential equation, so I tried to draw superimposed on there the two peaks before the interaction and after the interaction, okay? So it's not really particles, but there is this kind of dual interpretation of them, okay? So back in 71, shortly after the KdV equation was discovered to be integrable, Zakharov, he raised this weird question, okay? And so, you know, one of the things that happened in 2003 while I was visiting was that Carlos was running this seminar called Weird Things Seminar. And so, Weird Stuff Seminar, yeah. George. Okay, so George was a great seminar with many different things going on. And so, anyway, this is a weird thing that we didn't talk about then, but it's a... It definitely, yeah, yeah. Okay, so he suggested we should imagine a dilute gas of solitons, and I will spend the rest of the talk trying to explain what I think that means. Okay, but the starting point is what you just saw, numeric, which have been posited in there, and when you compute then sort of what the effective velocity should be, you arrive at this equation, that the velocity of this fast-moving tracer soliton is no longer a constant, but it's sort of being accelerated by this gas of solitons with which it's interacting. Okay, so in the process of describing this, Zakharov sort of suggests there should be some randomness. But he doesn't make it precise what is meant by the randomness that you should introduce into this system of equations. And also he sort of suggests that the gas of solitons should be a bunch of peaks that are well separated so that this tracer moving through them can interact with them one at a time. Okay? Those are sort of caveats in the original description, which were later kind of in 2003, Gennady and collaborators managed to generalize. So this is Zakharov's equations. So it's a pair of equations, one for a density of solitons and the velocity of a tracer soliton with arbitrary given velocity, how it is adjusted by interacting with the gas. Okay, so he called that a kinetic theory of solitons, and Gennady and collaborators generalized it to really a coupled system of equations, where you need to try to solve this pair of equations for S and F. Okay, and that was, so what I've described is what was analyzed for the case of the KdV equation, but it's been extended to all of the integrable equations that I mentioned and many more. Okay, it's a strange thing because the PDE itself is completely integrable, so you should be able to prove everything you want to know about the solutions of the PDE, but there's somewhere in the background one is interested in introducing randomness into the picture. And once you introduce randomness into the picture, it's much harder to say something about expected values, fluctuations, and the like, okay? So there's this, just a good review paper that was published in 2024 in Phys Rev E by Pierre Siret and collaborators that explain sort of where things are as of that date. And it has the theoretical description of what I just gave you, basically, along with numerics and experiments. Okay, but if you're an analyst, then these questions start to arise. So this is just a list of questions for which there are some answers and there are some things that are still wide open. So do solutions of the PDE actually obey this system of equations that I derived? That's sort of the fundamental driving question for what I'm talking about today, okay? Another question is, what does it mean to have a gas of solitons when you're really studying a solution of a nonlinear partial differential equation? And is there the possibility to carry out a precise analysis of a tracer soliton actually flowing through what you might consider to be a gas of solitons, but from the context of actually solving the nonlinear partial differential equation? And, okay, what is the correct way to introduce randomness into this analysis and to study fluctuations? How good are the numerical simulations when you're trying to study this problem with a large number of solitons? Are there any interesting predictions for the original PDE, which is already integrable, from the kinetic theory? In the case of randomness, the answer is probably yes, but otherwise, no, you can prove everything because it's an integrable system, okay? And then, can you use this language to describe non-integrable or nearly integrable systems, provide a kinetic theory of soliton gases when you don't have an integrable equation? That's a very, crazy question, maybe. Okay? So it's probably good to show you some pictures. So this is now not the KdV equation, but the nonlinear Schrodinger equation. You're looking at the absolute value of the solution at t equals 0 up there. And that's a particular solution which is described spectrally by this picture here. I'll say more about that, but I have 65 solitons embedded in this solution. It's a precise 65 soliton solution, and you're looking at the plot at t equals 0, at t equals 10, and then by the time you get to t equals 50, all of these 65 solitons have sort of spread out, and if you were to count all of these peaks, you'd see exactly 65 of them, and they're really now in the kind of long time asymptotic regime. They're all very well separated and spreading apart. So what's being asked by this kinetic theory is there a qualitative description of this picture for moderate timescales? Can you say something about what is going on in this region of time over macroscopic regions in space? Okay? It's an asymptotic analysis problem in which the number of solitons in the problem is growing to infinity. That's the asymptotic parameter. Okay? So here's a movie in which there's 66 solitons, and so you see the red dots are the original 65 of them, and then there's one extra green dot in the upper and lower half plane that corresponds to a tracer, and I would like to enjoy watching this tracer soliton propagate to the left through this gas. Okay?
Should we always imagine the tracers going faster than anybody else?
No, you can change that, and actually the tracer can have its velocity drop to 0 and reverse backwards. It depends upon how you prepare the gas of solitons, what happens to it, okay? In this one, yes. So amongst the weird questions that you have to ask is, how do you define the location of this tracer? The natural idea would be just to find the global maximum and call that the location of the tracer. But let me pause the solution just for fun, okay? This is, so if I try to drag this a little bit, you'll see that, right there. No, that's the end of the run. Sorry, let me do this again. So you see that's somehow the global maximum jumps. So it's a little bit strange to ask for a particle interpretation when it's hard to make a precise definition of the particle's position, unless you choose the parameter so that there is always exactly one global maximum. Okay, so this plot is chosen to demonstrate that that's a little bit weird, unless either you choose the parameter so that the peaks are large enough, there's always one global maximum, or you come up with another definition of the particle's position. Yeah?
Yeah, I think that's right. I think I got distracted with the beautiful pictures. You showed the elastic collisions of the solitons first, right?
Uh-huh.
So here, it's not elastic, right? Is it elastic? I mean,
So it depends on who you ask. I say no, but yeah. So what you have here is these peaks here. They're kind of the remnants of a large number of solitons that are not separated. So it's really some kind of looks like a conoidal wave.
because they're not separated.
Because they're not well separated.
Okay.
And then this one peak is kind of pushing through them, and as it's pushing through them, it's being accelerated a little bit. And so it's not really an elastic interaction. In fact, when you say elastic solitons interact elastically, what you're really saying is that you go from time is negative infinity to time is plus infinity and compute everything. Then it's a nice interaction. But if you have finite time interaction, it is not elastic at all.
Yeah, and I think you said a magical word for my intuition is like more like a conoidal wave, and you see like the period is changing a little bit after the tracer went over, right? So,
Yeah, it's an interaction.
okay,
Yeah,
thank you.
yeah. Okay, so that kind of raises the question: what do you mean by a tracer? How do you define its position and its velocity? And is there any sense to talking about this? And that's where maybe randomness comes in and saves the day a little bit. Okay, unless things are really extreme enough, there's always a unique peak which you can identify with the position of the tracer soliton. Okay. This is just a snapshot of those a snapshot from the previous slides, okay? And again, the question is there a qualitative description for this for moderate times? It's just repeating myself now, it's a strange kind of question because the system is completely integrable, but you're looking for a qualitative explanation which describes maybe a coarse-grained picture. Can you describe the average velocity of this peak as it propagates through and how it couples to the kind of evolving density of soliton parameters? Something like that, okay? Okay, so how do you talk about n-soliton solutions of a system of one of these nonlinear partial differential equations? So you have to bear with me for a second. I'm going to describe it for you. This is a Riemann-Hilbert problem, okay? It's the inverse problem that comes from that's actually the Lax operator for the KdV equation, which is the Schrodinger operator. But here is a problem in complex function theory. Find two functions, m1 and m2. There they are. Okay, so I found them. So they satisfy a bunch of conditions. So m1 and m2 are both, in this case, meromorphic functions in the plane. Okay, they have poles. So the first function m1 has got poles in the upper half plane at each of these pole locations. Those correspond to L2 eigenvalues of the Lax operator. Okay, which I'm avoiding defining in the interest of time. Okay, and m2 has poles at the complex conjugate points in the lower half plane. Okay, and the poles, in order to describe the behavior at the poles, we usually say something like this. The poles of the first entry, M1, there are residues there, and the residues are related to the values of the second entry at those poles. And so that's described in this formula in the upper left-hand part of the screen. The residue at each of these points, I, kj, of M, is given by, it's actually the second entry of M times this constant, which you see inside the matrix. And the lower half plane, this formula, strange-looking formula here, is characterizing the pole, the residues in the second entry, M2, in terms of the values of the first entry. Okay, so it's a strange sort of, but it's actually a system of linear equations which you can solve for the residue for the residues. Okay, and since it's a pair of meromorphic functions in the plane, it's just got n poles in the upper half plane, n poles in the lower half plane. It's a rather simple thing to look for, except that we're interested in the behavior when the number of poles goes to infinity. Okay? Cool. If you can find M1 and M2, then this formula here is the way in which you can produce the solution of that PD in the upper left-hand corner. Okay? You just take a moment at infinity, and that gives you the solution. Okay? Cool? So you see a picture like this, you think that determines a solution of the partial differential equation by this procedure. Okay? So in the case of the KdV equation, what you're looking at is sort of suggestive, right? You can imagine having an interval in the upper half plane and poles accumulating on that interval, and then the complex conjugate interval in the lower half plane, poles accumulating on that interval. And the question is, what happens when n goes to infinity? And that was carried out in this work that I'm pointing at by Manuela Girotti, Tamara Grava, Bob Jenkins, and myself. And the important feature is that in all of those residue conditions, you see this, there's this 1 over n, r divided by n. N's the number of poles, and as n grows, of course, that's getting smaller and smaller and smaller. 1 over n, I mean, is getting smaller and smaller and smaller. And that's helping to manage the analysis, okay? Okay. So now I'm just pointing out what I've described as kind of a first instance where you can imagine what is a soliton gas. I've got a large number of poles. Each pole corresponds to a soliton. As n, the number of poles, goes to infinity, I'm really creating an infinite collection of poles, so a gas of solitons in some sense. And so this is now a slide that describes a gas of solitons plus one extra soliton, the green dot being the extra pole, which is an extra soliton, okay? And then there are a collection of poles accumulating on the band in the upper half plane and the band in the lower half plane. And the question is, after taking this limit, what is the behavior of this one extra soliton as it interacts with this limiting gas of solitons? Okay? So I'll just show you a movie. I think the movie is next. This is a plot of our asymptotic analysis, okay? So the distance between this lone soliton and the gas over here, that's the asymptotic parameter. You have to wait a long time for them to interact, and that long time gives us the long time asymptotic analysis, which we can do. And as time is evolving, what is happening is the gas is forming a kind of a modulated elliptic wave here, a fixed conoidal wave out here, and the soliton, as it is moving now, it's got fixed velocity. Okay, the velocity of the soliton propagating in a vacuum is constant, but once it starts to interact, its velocity is actually going to change rather dramatically. It's going to become very oscillatory because it's going to interact with this gas. Okay, so we can watch it happening. It's hard to see that the velocity, but you just follow the peak, and you start to believe, okay, maybe it does not have a constant velocity anymore. It's actually accelerating and decelerating and accelerating and decelerating, okay, until it reaches this fixed conoidal wave region when it's still oscillatory. The velocity is oscillatory, but it's now got a constant average, constant mean, okay? Whereas when it was over here, the mean was slowly ramping up, okay? Yeah?
Quick question. Why does the tracer amplitude decreases over the peak of the gas and increases at the trough?
That's, okay, I mean, the short answer is I don't know, but it's like we compute it, right? What we actually compute is the asymptotic behavior of the solution. It has one element which comes from the background, which is this elliptic wave, and another element which comes from the additional pole, which is the soliton. And when we compute the amplitude, it changes in time.
Yeah, no, but it's funny when it's the highest, it sort of goes down.
Yeah, it's true. I don't have an explanation for that. Okay.
Maybe easy
Yeah.
question. Why does the gas stay still?
Oh, beautiful pictures.
Say it again.
Why does the gas apparently stay still?
It is slowly moving to the right.
It's just moving much, much slower.
Much slower than this thing. I mean, the difference in velocities is something like a factor of 8. between them. But if you watch it, it is slowly moving.
See if it's stretched out a little with the left.
Yes, I thought it was in the reference frame of the gas.
No, this is fixed. So you see this, it's very slowly moving that way. Okay?
But do all those solitons have the same velocity so they stay working?
No, they're different. So this is actually, like you'd like to believe this is a single soliton, but this is all actually a collection of solitons that are overlapping, and what you're looking at is some kind of a nonlinear mode that comes from adding up a bunch of solitons. Okay, so you can describe it asymptotically as a kind of deforming conoidal wave here, a slowly varying conoidal wave whose parameters change slowly over here, and eventually you get constant parameters over here, but it's traveling that way very slowly. Okay? Okay. And this is a plot of the velocity of the peak. So we chose parameters so that you can prove that's a global max at all times, a single unique global maximum at all times. And what you're looking at in blue is the velocity of that global maximum. Okay, it's the asymptotic description of the velocity of that global maximum. We have a formula for it, and we just plotted it. And then the black curve is the spatial, is the temporal average. Okay, and eventually it's constant in this region where it's interacting with the fixed conoidal wave. And it turns out that that black curve solves the kinetic theory. Even though there's no randomness, we've managed to show in this particular example, or collection of examples, that the kinetic theory is validated. Okay, so there's a description of the density of this gas and the velocity, and you couple them together, and it actually solves it both numerically and also analytically. Okay. But there is a weakness in this, which has been resolved later. The weakness is that what I described, remember I said, you've got to wait a long time for this interaction to take place. So that means there's an order of operations that I'm forced to confess to, which is first we let n go to infinity, and then we do a long time analysis. And that order of operations is easier than the joint asymptotics, which I would like to be able to do, which is where n goes to infinity while t goes to infinity, or let n go to infinity and then see the dynamics at compact length scales in x and t. Okay, which has been resolved, but that's what comes next. Okay. Okay, so this is just a short, whoops. In case you're interested, this is the formation of that soliton gas that I was describing before. So this is with 4 solitons and then 8, okay, et cetera, up through 128. All right, and down below is the picture with 64 solitons. It's important to notice that the plot actually has got exponential decay here, and out here eventually there's exponential decay. And as n grows, it's a fundamental question. What is the region in which you're seeing exponential decay of the solution? That region is actually growing. I mean, it's moving out as n grows. And how that scales is a fundamental question, which, okay, resolvable, but has not been written down. Okay? Now, what is this picture on the top? Those are not individual solitons. Actually, because all those residue conditions are order 1 over n, that's actually the accumulation of all of the tails of the soliton. The fact that the residue conditions all are small means the center of each of those solitons is actually being pushed very slowly out in one direction. Maybe it's this direction. And they're really located a distance away from the origin that's like logarithmic in n. But near the origin where this is being plotted, they're all kind of... it's all of the tails that are accumulating to give this strange-looking conoidal wave. So it's not the actual peaks of the soliton, it's the accumulation of the tails that's giving this conoidal wave. Okay, and that is part of the reason why we needed to take n to infinity first and then let t go to infinity second, because it was easy to do the analysis when the residues were all of this size, going off to 0. Okay, so but more recently. Guido and Aikaterini, so Aikaterini Gkogkou and Guido Mazzuca, who are postdocs at Tulane, they study this same problem, focusing nonlinear Schrodinger equation, with poles as accumulating, as you see there, on a finite interval in the upper half plane and the complex conjugate interval in the lower half plane. This is now for the nonlinear Schrodinger equation instead of the KdV or modified KdV equation. But the important thing is the residue conditions, which are very similar looking, are no longer 1 over n. So we're staring right at the heart of the beast. All of the solitons are accumulating in an open region near the origin. Of course, they're being pushed around a little bit, but we're not looking at the tail, okay? And these guys figured out how to carry out the analysis. It's a lot of Riemann-Hilbert machinery and trickery, which I'm not going to tell you about. Okay, but here's a cartoon description. So there is a kind of a typical solution, which is called the soliton gas solution, which still has n dependence in it. So this is sort of after a large n analysis, you have a solution which depends on x, t, and n. And where is the n dependence? It's just right here, this logarithmic constant term. That's really the only place where the n dependence appears, but it's still a function of x and t and n. And then the finite n soliton solution is very close to this object. Okay, so this is really what Guido and Katerina worked like crazy to prove, is that the difference between the n soliton solution when n is large and this specific object is 1 over n. Okay, that's sort of the brutal result, but it says that for finite values of n, you can actually see the formation of a soliton gas. Okay, and this is the analogous picture in there. In that case, it's funny because it does not look very different, but the main difference is it's much more regular. It's a surprising fact that it's much more regular than the previous case. All right. And yeah, so since I made these slides, actually, we've managed to study the interaction of a single soliton with this, but I won't tell you about that. It still satisfies the kinetic theory, but it's sort of not as interesting yet. Okay. Andre, how much time do I have? Like an hour left?
An hour and quite. I have 33 minutes
okay.
off the clock, which means, right? Yeah,
perfect.
27, but leave some room.
Yeah, okay. Thanks. Okay, so now I'm talking about the nonlinear Schrodinger equation, okay? And I want to try to construct a gas of solitons in which there's randomness so I can really talk about fluctuations. That's the last topic. So it's all soliton gases, which means finite numbers of solitons, no reflection coefficient. I'm assuming that the reflection coefficient is 0. It's just a bunch of solitons, but I want to take them to be random, and so that's why you see this, the plot there no longer in a kind of ordered fashion on the upper left-hand corner, okay? So it is a question, how do you embed randomness into the problem? And so the first way that we're doing it is by taking the locations of these poles, which are the locations of the L2 eigenvalues for the Zakharov-Shabbat operator, to be random. And we take them to be IID, and the distribution can be anything, but they're IID in some domain of the upper half plane and then complex conjugate in the lower half plane, okay? So the basic questions are to describe the average behavior of the solution and also the fluctuation of the solution. And I will sort of try to cut to the chase without telling you too much, but there's a little bit of interesting Riemann-Hilbert analysis to tell you about so I can make a contact with the so-called vanishing lemmas, which Charlie mentioned about Carlos's earliest works, okay? So bear with me for a second, okay? So what you're looking at now is the Riemann-Hilbert characterization of an n-soliton solution for the nonlinear Schrodinger equation. And the pole locations, you can see how wild and random they are by the fact that they're kind of no longer on a straight line. Okay? And the first canonical move that one does in studying Riemann-Hilbert problems with poles, meromorphic Riemann-Hilbert problems, is to remove the poles. And so I'm not going to describe this to you, but this transformation from M which is the original unknown, to A, okay, is intended to remove the poles. So A, as a new matrix-valued function, no longer has any poles in the plane. But of course, it has jumps across these curves. You defined it in a piecewise analytic fashion, and then it's removed the poles by some magical algebraic calculations that I'm skipping. But the price you pay is you have then jumps across these curves. If you can find A, you still get to determine from this unknown A of Z the solution to the PDE, okay, through this weird formula. So A, of course, outside of the curves, A is still a meromorphic function. There it is. If I knew what these alphas and betas were, I would be able to describe the solution of the PDE, which is here, okay? So my objective is then to give you an asymptotic description of the betas so that I can tell you what the asymptotic behavior of the solution of the PDE is, and then study it with study fluctuations. All right? This is the Riemann-Hilbert problem that A satisfies, and it still has randomness because those ZKs are random. But what you're looking at in that jump relationship is a linear statistic. And we know a lot about these linear statistics. For example, the average of this random sum is actually deterministic and independent of n. It's just this integral right there. That's exactly one of the reasons why there's a 1 over n floating around, is so that we can take averages and get something which is independent of n and explicit, okay? So that immediately tells you what we ought to do is replace that sum by its average and study that new Riemann-Hilbert problem. Okay, so instead of A, I'm going to call it fancy Z. Okay, and that's the Riemann-Hilbert problem for fancy Z. The brackets means I've averaged. Okay, but okay, here's the strange thing. The average, if I were to average the solution of the PDE, it does not solve the PDE anymore, right? If I have a random solution of the partial differential equation and I take the average, what I get after averaging no longer solves the PDE. However, what I'm doing is different here. We're averaging the Riemann-Hilbert problem. So this new Riemann-Hilbert problem, if I know it has a solution, I've got a new kind of regularized solution of the PDE, okay? But I do not have an existence theorem off the bat. I don't have any a priori knowledge, so I need some kind of a proof that this problem has a solution, which is a version of the vanishing lemma, which goes all the way back to the beginning of the analysis, okay? And can you describe the average behavior? Does the average behavior of this difference go to 0? And okay, can you describe the fluctuations? Those are the questions. And I should mention it's similar in spirit to work of Ding and Tom Trogdon, who developed the perturbation theory for orthogonal polynomials. It's kind of this in very similar types of calculations. Okay. I'm still okay, so I feel like I shouldn't drag you through all these calculations, so let me not, okay? What I'm doing is creating the Riemann-Hilbert analysis of the difference between psi n and that psi, okay?
The slides are great.
They're even better, yeah, sorry about that. Did it disappear permanently now?
Yeah.
Okay. It's better when they're blank. So the maybe one feature to tell you is there's like now canonical step 2 and canonical step 3 in Riemann-Hilbert analysis, which is to compare capital A to capital Z. And you compare the two by forming A times Z inverse, which is right here in the middle, and asking, can you describe the Riemann-Hilbert problem that new object, which is the error called E, satisfies? And okay, you can just step back and stare at this and say, oh, what appears in the middle of this Riemann-Hilbert problem is the difference between the random linear statistic and its average. That's nice. As long as this minus this is small, we probably can invoke a small norm theory. And that means you have to ask probabilistically, what is the measure of the set where this is not small? So it becomes really a question of probability theory. Can I estimate the the probability that this is not small, and then jam that into a small norm theory for Riemann-Hilbert problems. And that's what we managed to do. And so so there's a small norm theorem that says if this quantity here in brackets is small, then solution exists and satisfies a bound like this, okay? And that's enough to prove that the difference between psi n and the, so this should be just psi without an n, is actually small, okay? Good? So I'm going to skip now to the punchline. So very recently, Manuela Girotti, Tamara Grava, Joseph Najnudel, and myself managed to prove these three results. So psi n converges in probability to psi. The average of psi n converges to the limiting behavior of psi itself. And there's a central limit theorem. Okay, that was sort of the hardest part of the proof, was to prove that the difference psi n minus this psi multiplied by root n has a central limit theorem. All of these are under the assumption x and t are in compact sets. So you fix a compact set, you can prove all these results. If x and t are in sets which grow very slowly with n, it still holds true. But the interesting really thing to do next is to try to understand the behavior of these fluctuations when x and t are growing at a sufficiently large rate that it's no longer Gaussian. That's what's really interesting, and okay, that's ongoing. Okay? And so the future objective is really to study the fluctuations when x and t are growing sufficiently fast with n that you don't have central limit theorems. Okay? Is it going to be Tracy-Whittem type results or something else? We don't know. Okay? So this is like a summary slide before I stop. Okay, so do solutions of the PDE actually obey the kinetic theory? That's the first question I was raising, and there's a lot of evidence that says yes. In the case that I described for you, the deterministic case, no randomness, a tracer plus a gas, we have analytical proof that the answer is yes. There's a lot of numerical simulations, and I am required by losing a bet to mention the glorious Thibault Congy and also Giacomo the glorious Roberti, who have done significant numerical experiments which demonstrate with randomness that, that solutions of the PD actually obey the kinetic theory. Okay? What's still wide open is to study these problems when t and x scale with n. And you know, the state of the art numerically, even with the glorious Thibault and Giacomo, is like 120 solitons. N is equal to 120. The moment the system is very badly posed, and so if you try to get n much larger, it just doesn't give you meaningful solutions. So that's sort of a good numerical project, which use Riemann-Hilbert analysis to prep the problem so you can study, with 2,000 solitons, something like that. But that's also in the future. And then here's a question which, does the kinetic theory make meaningful predictions about the PDE? And that is a place where so far there hasn't been much done about that. It's a little weird because you have a completely integrable PDE. You can say everything you need to know about it. The only way that predictions from the kinetic theory are going to be meaningful is if you say something that has to do with randomness. So what is the average of the field, mod psi to the power 4? That's the kind of calculation that I don't think is done in the integrable system literature. And maybe with the kinetic theory you can make a prediction and then test it. Okay? And of course, can you extend that to non-integrable equations? It's a little weird because most non-integrable equations don't have n-soliton solutions, but there's enough language around that maybe it's a meaningful thing to ask in the perturbation of integrable systems type of questions. Okay, and so I have one more photo to show you. So that's all I want to say. But thank you again, Carlos, and happy birthday. I think this properly summarizes our experiences with Carlos.
Thank you. Thank you very much, Ken. So, questions for the questions?
I have something that is full. sort of a comment, but it could go on forever. So you're more than entitled to break at any moment. Right? One of the many interesting, very interesting things you stated in your lecture had to do with the fact that we shouldn't think of solitons as each hump being a soliton, right?
Uh-huh.
And you know how total goes, right? You start with n particles on the line, you label them, then you go flashka, you get a tridiagonal matrix. Along the diagonal, there are the velocities of the first, the second, the nth particle, right? And then, if you go to minus infinity in time and plus infinity on time, okay, there's an inversion of the velocities, right? Which, of course, if you interpret by saying that each index is a particle, right, is completely different to the idea that the same particle is the fastest in the past and in the future, right?
Mm-hmm.
The whole story gets paradoxical, right? So I found it very interesting that finally somebody is raising an issue, right? What's really the identification between solitons and particles? It's not so literal, right?
É. E aí, bicho? Beleza? Yeah. I think for us, the weirdest part was when we said we should just track the position of the global max, and then it clearly jumps. Right? So.
It's pretty much like you're evolving with a tridiagonal matrix and you see large numbers going across its spine, right?
Yeah.
It's weird.
Yeah.
Yes, please.
Yeah, on this look, I don't get intuition on this. What you're randomizing over, what you're randomizing over when you're moving the poles, and then like, how do you think of this as being some of the soliton parameters?
Yeah, so the poles, those really are the L2 eigenvalues of the Zakharov-Shabbat operator, and they encode the solution. So whenever I draw a picture and show you a bunch of poles in the plane, you should think, oh, that's describing in an implicit way the solution of the PDE. So I pick them once. They're usually they stay constants in time, but they determine the solution which evolves in time. Okay, so by making them random, I'm providing a small collection of random initial data for the PDE. There's like two pieces of information. There's the locations of the poles and then an associated constant for each of those poles. I'm not making those random. Those are kind of deterministic. I'm randomizing the pole locations, which is sort of half of the parameters that describe these n-soliton solutions. Okay.
You can claim every time you add a pole that you're in spirit adding a soliton.
Yeah. And you only see them as individual solitons if you wait, either t goes to negative infinity and then they all separate out and you see n peaks that are very far apart, or you go to plus infinity and they separate out and they're very far apart. And we're interested in the behavior in the intermediate regions where they're not separated. Thanks.
Okay, so we first remind you that we have a coffee break. We come back at 4 for last and very interesting topic today. Then let's thank both speakers. I have to let people go.